So isotopes, they are atoms of the same element, but they have different masses. And the reason they have different masses is because they have a different number of neutrons. So again, you cannot change the number of protons without getting a new element, but you can change the number of neutrons. And neutrons have mass. They are not negligible like an electron. So it's going to influence the mass of an atom. So when we talk about isotopes, we often use this notation. So we'll say carbon 12 and carbon 14. These are common isotopes of the element carbon. So the 12 means the mass. So when you look at a periodic table for carbon, the mass reported is 12.01. So it is not 12 and it is not 14. It's an average between them. But unfortunately, or fortunately, I guess, it's not just an add them together and divide by 2 kind of average, like the mean. It's actually what's called a weighted average. So if you've ever tried to calculate your mark, let's say in high school, it can be a little bit frustrating because we have to consider the weightings of the categories. We don't just add up your test mark and divide by how many tests we write, right? That's not what we do. So the same sort of thing exists here, and it makes sense. If you have 2 isotopes, that means in the Earth, there is some carbon 12 and there is some carbon with a mass of 14, so it has 8 neutrons instead of 6. Then in order to make the atomic mass that we're going to use when we get to quantities in a useful way, you want the average to reflect the carbon that is probably in your sample. So you have to take into account the abundance, or how much of it there is. So we're going to look at a way to calculate the average weighted atomic mass for the elements based on the percentage in the world. So if you have a weighted average, then it's going to reflect which mass, so whether there's 1 isotope, 2 isotopes, whatever, that is most common. So because on the periodic table, carbon is 12.01, that's closest to 12. That means in the Earth, on the Earth, whatever, in the organisms, we are all made of carbon. There is more carbon 12 than there is carbon 14 because the average is closer to that. So when you have this, that means this is the atomic mass. Let me see if I can make that bigger. So there's no way you would never be asked to memorize the isotopes. Some elements only have 1, some have 2, some have 3. Some are stable, some will decay to release nuclear radiation. So there's no way looking at this periodic table to know. So that's why we use this notation, because we want to tell you the mass we're talking about, or the isotope of carbon we're talking about, is carbon 12. The isotope we're talking about is carbon 14. So when a number is written at the end like that, that means how heavy that isotope is. And then you would just follow the same ideas. So 6 is the atomic number, and then you would just do 12 minus 6 to get the number of neutrons. 14 is the mass. 14 minus 6 is 8, okay? So you can't just be told carbon has 2 isotopes, how many neutrons would each have? You have to be given more information. It has to tell you what the mass of those isotopes are. Could you look at the average? It's 12.01. Okay, I'm going to infer that there is an isotope that's 12. Sure, but that's a very tricky thing to do, and it's not practical. You would never have to do something like that. And again, if you're into science or you're into scientific reading, carbon 14 is actually the isotope that's used in carbon dating. So, maybe you've read about, and they'll literally use that terminology. Carbon 14 is used in dating. So for example, like if you find a dinosaur bone, like a fossil, then it's not like you can say, hey, dinosaur bone, what was your birthday, right? So what they can do is calculate how much carbon 14, which is a little bit radioactive, every living carbon-based organism has it, then they can calculate that using the half-life to figure out how much is left. So usually they won't say the dinosaurs existed in November 2020. They give, so many millions of years ago or whatever, a broad idea of when that organism was alive. So any sort of fossil, plant, anything that had living matter, rock, then it can use the amount of carbon 14 left. So when you take 11U math, you're actually going to learn how to calculate half-life. It's an exponential function, and it's actually pretty straightforward. It's not that hard to do. So everything that breaks down that has an isotope that will decay, we call it breakdown, then it does it characteristically. So it lasts for so long, and then half of it will decay over 5 days, 1,000 years, whatever. They can do the opposite thing for, say, bacteria. So bacteria can multiply or double however many days, or usually bacteria is hours. So they can make predictions about what the viral load is of something or whatever based on how long they've been sick. So looking at this kind of math is really useful and practical, and you'll do that in 11U math. So if you haven't taken 11U math yet, I know some of you have it next week, then that's one of the topics you'll talk about. But here we're not, because 11U math is not a prerequisite, we're not going to actually do the calculation for the half-life, okay? So some of the isotopes we exploit the use of all the time. So this picture's not in there, but there are 3 isotopes of hydrogen. So carbon has 2, hydrogen has 3. Again, there's no pattern, there's no rhyme or reason. Sometimes they're just discovered to have a certain number of isotopes. There's never a time when you're going to have to memorize how many of each there are, nothing like that, okay? So the isotopes of hydrogen are very well studied because the first isotope, which is what you're used to, 1 proton and 1 electron, 0 neutrons, is called protium. Deuterium has 1 of each, 1 neutron, 1 proton. And then tritium, again, if you're a history buff or you do scientific reading, this is the isotope of hydrogen that's used in the hydrogen bomb. So this isotope, when it decays, releases so much energy that you can blow up cities, etc. So some isotopes are really well studied. These ones are even given common names, and some just aren't. And there's no way for you to memorize that. It's not a practical thing you're going to need to do. Okay, so how did they discover either the relative abundances, the different masses? So this is called a mass spectrometer. So in grade 9, we talked about the flame test. You might have also looked through the little black triangle and split the light into different colors. Did you guys do that? Like lines, a graph, basically. So anytime you produce a graph, you can call it a spectrometer. So instead of light, this is a graph based on mass. Okay? So what happens is depending on the computer putting out the graph. So this is the atomic mass. So zirconium has 1, 2, 3, 4, 5 isotopes. And so it's like a normal graph. It increases this way. But it also tells you the abundance. So the most abundant isotope is zirconium 90. And then if you look, zirconium's atomic mass is 91. So the highest one is 90, or an average. 90, the lowest one is 90, the highest one is 96. That's a pretty big range. So its weighted average is closer to the lower end because this is the most abundant. Okay, that kind of thing. Not that you're never going to have to draw these, okay? So it's really actually simple, and it sort of is like that cathode ray. All you have to do is bend a beam. And the beam, instead of bending it based on charge, now they're bending it based on mass. So you can even think of it like if you had a hair dryer and you turned it on and you had something heavy, the hair dryer would not be able to move the heavy thing very far. So it would hit the detector with showing very little movement. Then, if it was light and you put a hair dryer on it, like say a ping pong ball or something, then that ping pong ball would travel really far because it's so light. So again, it would be detected in a different spot. So then a computer can analyze it, and it's just saying heavy, light, how heavy, how light. Okay. So you have to have a source. The source is deflected based on size, and then the computer determines its mass. So you wouldn't do this by hand, okay? I just wanted to show you. Okay. So many isotopes are naturally stable, but many are not. So others will break apart to produce nuclear radiation. They are called radioisotopes. I left a humongous blank, but really it's just for this. And radioisotopes get a special name because we exploit them to use them, and also they're sort of a part of like superhero lore. Sometimes lots of superheroes seem to get their powers from being bombarded by nuclear radiation. That would not be a thing. Nuclear radiation destroys cells. It doesn't make them stronger. Not yet anyways. We haven't discovered any. Maybe that'll be your PhD project. Okay, so there are 3 common forms of radiation. So the first one is, and they're in order of weakness. So this is the Greek symbol for alpha. Maybe you've seen it on the back of a car with Jesus inside it, that like the alpha is Jesus. That's why they use it. So it looks like a helium nucleus. It's a package of energy with 2 protons and 2 neutrons. You can block alpha particles with paper. So, not that strong. Alpha particles were a common initial study tool. Paper is not a big deal. And then people like Marie Curie started to try to use stronger chemicals or substances, compounds that would release nuclear radiation. And unfortunately, they became sick with radiation sickness because they didn't know that there was levels, right? So beta radiation or beta particles, again, that's like it looks like a little bee with a tail. And they are represented by a negatively charged electron. So a little bit more energetic, a little bit faster. And they can pass through paper, but not aluminum. So if you go to get an x-ray even, sometimes you wear that lead vest, or it's like heavy because it's trying to block the beams of energy getting inside cells that you don't want it to. You want to take a picture of your teeth, for example, not your chest, or vice versa, whatever. Usually the person doing the x-ray is not in the room with you. They're somewhere else, right? Because they don't want to be exposed to the radiation or the energy. And then the last one is gamma. So this one is, this is the one that often superheroes seem to have no mass. That's bad English. Has no mass, sorry. Blocked by lead. So you could not be exposed to gamma radiation and turn into the Hulk. That's not a thing. Sorry. Sorry to burst your bubbles, but not yet anyways. It says we're going to watch a video here. I don't know what this is. Let's check it out. Oh, I think it's about Marie Curie. So this is kind of cool because it actually shows her. She's like standing by a huge vat. I think it's uranium, and she's literally like just standing there stirring it. So like uranium is what we use in nuclear reactors. Like this much will power cities, and this woman is just like stirring it, boiling it. So it's just so bizarre that she would think that's okay, because it's obviously not. So then it talks about Rutherford's gold foil experiment. We'll watch the rest in grade 12. Okay, so it talked about that her books are still radioactive. So again, when you have something that decays, it decays with a mathematical predicted half-life, we call it. So you can do the math and figure it out. So you could figure out when her notebooks would be safe enough to touch. You could see her working there, even though it was just a reenactment with Henry Becquerel. You saw him just like handling the uranium, and that would not occur now. So even when you go get a dentist x-ray, you wear a lead vest, right? They didn't have anything, so they had no idea what they were dealing with. Okay, so what do we use radioisotopes for now? So sometimes the killing of tissue is good. So for example, in cancer therapy, which is this picture here, you can, depending on the kind of tumor, you can have radiation. And usually you want it to be like a point source of radiation. So like a brain tumor that can be accessed maybe by the radioactivity, whereas something like leukemia, which is kind of all over the place, is more difficult to use radiation for. But you're trying to kill cancer cells, right? Kill tissues. Same thing with sterilization of food and medical supplies. So it kind of looks like the tubes inside are lights, but instead of fluorescence, it's giving off radiation. So one of the most common ways to kill bacteria is to heat something up. But there are obviously items that you can't heat up. You can't, boil lettuce and then give it out, right? Like that doesn't work like that. So that's why it's called cold pasteurization. Pasteurization is when you heat something really hot to kill the bacteria. So they can pass it through a cobalt-60 source. Cobalt-60 is a common isotope. It's easy to get. It's not that expensive. But you still have to handle it with care. Don't get me wrong. So, and then another thing, this one is specifically with the thyroid, but we use tracers in medicine all the time. If you've ever had a scan and you have to drink, maybe you're too young, but sometimes when they want to scan your insides, so obviously, let's say you're having problems with your intestines, it's not really useful to take your intestines out and be like, what's going on here, and put them back in. That's not how it works. So what they can do is use a tracer. So if you've ever had to have a scan and you had to drink like this weird chalky white liquid first or something like that, you're probably having to drink a little bit of a tracer so that they can see a clearer picture from the outside. So the thyroid kind of sits here in your neck, and the thyroid takes up iodine. So one of the isotopes of iodine, iodine-131, decays and gives off radioactivity. Radioactivity is easy to make a picture of. So you can see that these thyroids, so it's like a double gland organ. So this one, you can clearly see the two sides do not look uniform. That's not good. This one, you can clearly see there's this spot here. So possibly a tumor, maybe a dead part of the thyroid. It is not taking up the iodine. So the blackish spots, the darker spots, would be where the iodine is being used by the thyroid. Good. So it's not being used here. And then down here you can kind of see that it's not so good. This is like the starting, and this is like the end, There's all kinds of things with the thyroid, like it could be cancer, you can have hyperthyroidism, that kind of thing. So it's not, once they see the thyroid's not working, then you can do other tests to figure it out. So the same sort of, even, you could think of a pipeline like the pipelines in us. You can imagine if you had a blockage, 9, 10, 12 feet under the earth, what are you going to do, dig up the pipes every single time? No. So they can send a radioactive tracer, and wherever it stops, then that message can be sent to the surface because of the energy, and then you can say, oh, the blockage is here, this is where we need to dig, sort of more of a pointed source. Same thing with carbon dating. You can't ask a plant or a dinosaur, hey, when was your birthday? So we can calculate how much is left. and then extrapolate and figure out how much there was. Nuclear reactors, so there is in Ontario we have two. We have one in Pickering and one in Bruce County, a huge nuclear reactor plant. In the US, they rely a lot more on nuclear energy. We do have Niagara Falls for hydroelectricity. But nuclear reactors use radioisotopes. Depending on where you are, maybe polonium. In Canada, we can mine uranium, so often that's what we use because we have it. And then PET scans. So this is kind of cool. Positive emission topography. So what you can do is try to map the brain. So obviously, again, you can't take your brain out of your head and be like, hey, how's it working? And then put it back in. So what they can do is inject a molecule called glucose. So glucose is a sugar, and it's the only thing that can get across your blood-brain barrier. So that's why, like, if you are lacking sugar, like lacking food, then sometimes one of the symptoms is foggy brain or a headache because your brain's like, yo, where's my glucose? So what they do is they put a little bit of radioactive iodine on a glucose molecule and inject it into the brain. So it's sort of like red is hot and cool and blue is cold. So when you're resting, this is the back of the brain stem down here. This is the hottest spot. So the brain stem they call the old brain, which is like your basic functions. Things you don't even think about. Breathing, peristalsis, or whatever's just happening naturally. Then when you have, this is language and music, so you can see like white hot areas at the front. So people who have damage to the frontal cortex of their brain often have trouble speaking or reading or making sense of something they've read. Maybe they know the words, but they can't tell you what they mean, that kind of thing. And then you can see music as well. And music, so people will say, oh, this is like the old brain, like white hot. So music sort of, that came first. Like people were musical before they had language. So, that kind of thing. I think that's cool. But again, you're never going to have to draw this, okay? But you can see how your brain works. So then what they can do too is sort of map the brain. And if you have to have brain surgery, then they can use the map of your brain to make sure they don't touch parts in your brain that maybe have a vital function for you. So pretty cool. Okay, so the other thing you have to do is we're going to calculate average atomic mass. And remember, it's a weighted average. So you have to be given the abundance as well as the masses. So you have to be given the percentages and so this question is kind of unique. It really stands out because it's weird, okay? Often in a chart form, the questions in the homework, they're usually in a chart. It says like iodine 131, 90%, iodine 132, 40%. Again, there's no way for you to know or memorize or be able to figure out what are the different masses and what are their abundances. So you have to be given that information. Okay, so let's say, it's right there. You're given the isotope percentage. And so when you have the average atomic mass reported on the periodic table, we're going to consider both the masses and the relative abundance. We're going to use, for now, we'll just use U. That's what your textbook does, so we'll just stick with that, okay? So technically, when you write your answer to this kind of question, you should put U at the end, okay? If you put AMU, I wouldn't mark it wrong, but your textbook uses U. So when you calculate atomic mass, you just continue based on how many isotopes there are. Usually 2, maybe 3, maybe 4, rarely 5. So you just continue this procedure for all of the isotopes you're given. So basically what we're doing is taking the percentage, which we in math never use, right? You always divide by 100. So some of you will automatically do that without even thinking about it, divide by 100, which is fine. Then you have to multiply the abundance by that mass and add it to the other ones. So we have to take into account, it's weighted, it's not just add them up and divide by 2 like a mean. You have to do what is the percent abundance for that isotope mass. So like I said, it's often given in a chart, the mass plus its percentage abundance. So I made up this example. Cadmium has 3 isotopes. So you'll be given it like this. It'll say the name with the mass. Okay, this means mass. Sometimes it'll be given like this, right? So it's like kind of half of the atomic notation. And then you have to be given percentages. So cadmium 13 is 35% abundant. Cadmium 40 or cadmium 14 is 40, and cadmium 15 is 25. The total should be 100. Okay, that makes sense. Sometimes the abundances will be like 15.1 or whatever. It will be a decimal. Just use that. Okay, you don't have to round. It doesn't have to be a whole number. So then it doesn't matter. We're adding, so it doesn't matter what order you do them in. Usually it's given smallest mass in the form smallest mass to biggest mass. So like I said, like for example here, I'm going to divide 35 by 100. But if you're like, okay, that's obviously 0.35 and that's all you want to write down, that's fine. Okay, so you can decide if you're going to show all your work and you want to show what this is and what this is and what this is. You can do it all in your calculator if you have a good relationship with your calculator, all in one step. I don't care. For this one, because there's not a lot of space, I'm just going to write the answer, okay? So this comes out to 13.9. And remember, you want to do U. So if our masses are 13, 14, and 15, then our average weighted atomic mass shouldn't be 27 or something like that, right? It should be within that range there. So you can kind of check your answer. If you're given a real element and its isotopes, then you should be able to check with the periodic table and say, am I close, okay? So let's do a real one. So we'll do magnesium. Is everybody good? Yeah. I feel like 24 maybe got cut off. Sorry. So magnesium has 3 isotopes, 24, 25, and 26. And their abundances have to total 100. So again, you can be given decimal ones, that's fine, just keep the decimal. And then you're going to do the same thing. So 78.7 divided by 100 times 24 plus 10.13 divided by 100 times 25. Normally, when you do an actual real element, one of them is going to be way above the other one, or ones. I'll show all my work this time. You have a bit more space there. So usually your textbook rounds to 2 decimal places. I don't really care. You can leave all of them, but make sure you have U. So then again, you can kind of check, you go and look. Magnesium is 24.31. That's pretty good. I'm probably right. But again, you can check the logic too. If you got 10 and it's 24, 25, 26, then go back and check. You've done something wrong. And this is the kind of math where it seems really easy, but sometimes some calculators will do wacky things. So you really should get to know your calculator. You know, sleep with it under your pillow, take it out for dinner. Don't let anybody else touch it. If your brother or sister comes and says, hey, can I use your calculator? You can say, as Todd said, no. So don't, you'll be so much more successful if you use the same calculator every single time. It can be very frustrating for students when they don't know how to use a calculator. Obviously, if you forget yours, I have some I can lend you, but really try to use your own, okay? You'll be happier too.